Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on EDEXCEL Topic 17 Organic Chemistry 2. So this video is going to specifically look at the topics in, or the information in Topic 17. So if you're studying EDEXCEL Chemistry, then this is absolutely perfect for you because it contains all the information that you require and nothing more. So sometimes you can go through certain bits of resources and information online and wonder if it is for your exam board. Well, this is actually dedicated to you. In addition, this is obviously just Topic 17, but in the full range of revision videos for EDEXCEL for Year 1 and Year 2 on my Allery Chemistry YouTube channel. They're all for free, and there's information on there on whiteboard tutorials as well, looking at specific topics, and there's also exam paper walkthroughs, so it's quite a comprehensive range of information there for A-level chemistry. So all I ask, because it's all for free, so all I ask is you hit the subscribe button, and that'll be absolutely fantastic if you do that, just to show you support. And so long as people keep watching and subscribing to the channel, then I'll keep on making them. So also these, this is just a this is developed on PowerPoint, so you can actually have your own copy of these slides as well if you like. You can use them on your tablet and your smartphone. You can print them off if you want and use them as part of your revision notes. They're available to purchase if you just click on the link below. They're very good value for money. Click on the link in the description box and you'll be able to get a hold of them there. So, like I say, this is a revision video, so it's going to contain everything for EDEXCEL and has the basically the summarized points for Topic 17. It's quite a big topic. Obviously, there's three organic chemistry topics in EDEXCEL. So, Topic 18 is also organic chemistry. Some of the information is split across two videos. Okay, so let's have a look. The specification, like I say, it fits the specification for EDEXCEL. It includes topics such as chirality, carbonyl compounds, and carboxylic acids. So everything in here is going to cover these topics for this video. Okay, so what we're going to do is we're going to look at optical isomerism. Okay, so there's my hands there. My hands shouldn't be there at the moment, but never mind. So optical isomerism is a form of stereoisomerism, and they have the same structural formula, but a different arrangement of atoms in space. Now, you might have seen a little bit, depending on the order that you've done it in, you might have seen a little bit of optical isomerism within the transition metals video, or transition metal topic. This video, we're going to look at it in a lot more detail. And find out exactly what it is and about plane polarized light, etc. So, optical isomers are mirror images of each other and have a chiral carbon atom. Okay. So, a chiral molecule has 4 different groups attached to a carbon atom in the middle, and we can arrange these groups in 2 different ways. And this forms 2 different molecules, and we call these enantiomers. Okay. So fascinating. So these enantiomers are mirror images of each other and are non-superimposable. No matter which way you turn them around, they don't actually overlap. So these are quite unique properties that some molecules can have. But remember, it must have 4 different groups surrounding the carbon atom. Okay, so hands have a chiral center and they're mirror images, but they are non-superimposable. So you've got a picture of my hands here. So it's actually a short video clip. It's just to try and illustrate what we mean by when we say it's non-superimposable. Now you can see there, before I play the clip, you can see that they're mirror images of each other. You can see it there. Okay, so you can see, this is a mirror image of that hand, but actually they're non-superimposable. So let's have a look, see what I mean. So there we are. So you can see when we put the hands over the top of each other, they're not actually superimposed. They're not covering, the thumb's not covering the thumb, for example. It doesn't matter how much I rotate that, it's not actually going to cover that up. So chiral molecules in chemistry are exactly the same. These are mirror images of each other, but when we superimpose them or put them above each other, they don't actually fit exactly. So that's what we mean. So, for example, if we bring it back to chemistry instead of my hands, there's 2 molecules here. These ones are enantiomers of each other. And you can see we've got the mirror line down there, which is the red dotted line. And you can see these molecules are mirror images, and so therefore they are enantiomers. Okay. So, what we need to be able to do is find the chiral center. And we've got to draw a tetrahedral, draw them in a tetrahedral 3D shape, and we need to show them as enantiomers. So that's the first thing that we need to do. And you might be able to, you might be asked to do this actually in your exam, in terms of actually finding the chiral center, but actually drawing the 3D shape as well. So make sure you're familiar with 3D shapes and drawing them. You would have seen that in year 1 chemistry when you looked at 3-dimensional molecules or drawing them in 3D. So first of all, we need to find a carbon with 4 different groups coming from it. So let's have a look. So there's one group, that's the one on the end there. We've got a Br here. We have a hydrogen up at the top there. And we have our carboxyl group at the top there. So that means our chiral center is that carbon in the middle. So that is, that's the one with 4 different groups around it. You can see where I've color coded it. Okay, so then we need to draw this using the tetrahedral 3D shape. So you can see here, there's our first molecule there. So our molecule, this is the first molecule here. So this is drawn as a 3D shape. So all we've done is we've put the carbon in the center, and then we've put the 4 different groups that are surrounding it along the side. But we draw it as a 3D shape. So we put the wedges in, as you can see there, and we put our bonds there and our bond going away from us as well. So we draw it in the 3D tetrahedral shape. So then we draw the mirror image and we show both enantiomers. So there they are. So those are both enantiomers. So you can see we've got our mirror line down here, and we can see that these are a mirror image of each other, so perfectly. So these are enantiomers of each other. Okay, so optically active isomers, they rotate plane polarized light. Okay, and this is a method of actually detecting an optically active compound. So we basically shine light through the sample and see if it rotates it, but it's got to be what we call polarized light. So we're going to see how that can be made. So standard light oscillates in loads of different directions. So that's just like white light coming through the window. It oscillates in all sorts of directions of different colors, different frequencies, etc. So to different frequencies, should I say? And so this diagram here is just showing us the range of different ways the frequencies can oscillate. Okay. So then if we pass that light through a Polaroid filter, then what we get is plain polarized light. So we get light that only oscillates in one direction. So you can see here, here's our Polaroid filter there. So this is our light and coming in all directions. The Polaroid filter actually blocks some of the frequencies or some of the orientations coming through. And so only one plane of light will actually get through. And so then if we shine that through an optically active compound, then the optically active compound will rotate plane polarized light, and it will rotate it either left or right, depending on what type of enantiomer we've got in there. Okay, so it's a very straightforward method, really. You might not have one of these if you go to a school or college, if you've got access to a lab. You might not have one of these in school. It depends on obviously what type of equipment, but universities will definitely have these, of course. Okay, so one enantiomer, let's say, rotates light clockwise, and the other one will rotate it anti-clockwise, but they will rotate them by the same degree. So if one rotates it by 5 degrees right, the other one will rotate it by 5 degrees left. Okay, so now we're going to look at racemates. Okay, so racemates is actually where we have 2 enantiomers, but we have an equal amount of each enantiomer. Okay, so we have one enantiomer, which is enantiomer A, and enantiomer B. We have a 50-50 mix. So they do not rotate plane polarized light, and the reason why, and this might kind of make sense, is because actually the enantiomers cancel each other out. So remember when we looked at it before, we said that the enantiomers that rotate it right will rotate it by the same degree as the enantiomers that rotate it left. So because they rotate the plane polarized light by the same degree, then if we have both of them in there in an equal mix, then obviously they will cancel each other out, and you won't get any rotation of plane polarized light. So a racemic mixture of a chiral product is often made by reacting achiral substances together. So when the molecules react, there's an even chance of forming each enantiomer. Okay, so let's have a look. So you can see here, we've got our achiral substance here because we've got carbon with two of the groups are the same. Reacting that with bromine, for example, bromide ion, and then we form a substance which is now chiral because we have 4 different groups around that carbon. So we can either form that enantiomer or that enantiomer. So we can form it in different places. So we can form it in different areas, and obviously we produce HBr as well, because obviously we're reacting it with Br2s, let's say. So we can form these different types, but you can see chiral compounds are normally formed from an achiral substance, as you can see there. Okay, so we can see either of the hydrogen atoms can be replaced, and this is producing a mixture of the 2 enantiomers that we've just seen before. And so therefore there is a 50-50 chance of either hydrogen being replaced. So we make both of them enantiomers in equal quantities, the enantiomers that we've just seen before. And so here they are here. So what we've done is we've shown them as enantiomers and orientated them. So it shows them as mirror images so you can see them. So it's really difficult to adapt a reaction to only produce one enantiomer, and it can be quite expensive. And actually, enantiomers exist quite commonly in a lot of, especially in big molecules. You know, there's plenty of opportunity for enantiomers to actually be formed in bigger molecules, and it can be a bit of a problem. You might have seen a classic example was thalidomide, where thalidomide was used for morning sickness. Initially, that's how it was patented to be used as that, but it was made up of 2 enantiomers, and the problem was they used they basically kept both enantiomers in the drug, but one of the enantiomers actually caused deformities in young children, so when they were born. So clearly that enantiomer has had a very different effect to the other enantiomer was actually the useful part. You know, one of the enantiomers did cure morning sickness, but the other enantiomer, literally its mirror image, really caused a lot of problems. So this is really vital that we need to know, about the different enantiomers, and we need to know, will it cause an effect? Some enantiomers will have no effect at all in medicine, so what's the point in removing it? But some will, and that adds an extra layer of cost because we need to develop a reaction where it only produces one enantiomer is really expensive. So if we can get away with not removing the enantiomer, in other words, if it has no effect on people, then that's fine. So it is really important. Okay, so optical activity and reaction mechanisms, SN1. Now you will have seen SN1, SN2 reactions already. So you would have seen them within the probably in the kinetics reaction when you did multi-step reactions. So you would have seen an introduction to that. So you know a little bit about that already, or you should do anyway. So molecules with planar profiles. What these can do is these can make racemic products. So, for example, in SN1 mechanisms. So remember, planar means something that's flat. So it doesn't have any much 3-dimension there. So it's a flat molecule. So these reactions occur when we have an attack on the carbocation of a compound where a group breaks off. Okay, so we have a carbocation. Remember, carbocation is a molecule with a carbon that has a positive charge. The carbon has the positive charge. So let's look at the example where 2-halobutane, okay, so reacts with Y, as this is an SN1 reaction. The halogen breaks off and the carbocation intermediate is formed. So remember, with SN1s is we form an intermediate in these types of reactions. So let's have a look. So this is the first step. So remember, in SN1 reactions, the halogen here, this breaks off first, and then what we form, is a carbocation, as you can see here. So here's a carbocation with a halogen that's actually broken off here. A very typical SN1 reaction. So the reaction between Y and the intermediate involves attacking the planar molecule, and in particular, it's the carbocation that's been formed. So you can see here, what I've done is I've just altered this, twisted this round so it's kind of in your plane of vision or coming towards you, should I say. So the Y can either attack from the top, of this molecule, or the Y can either attack from the bottom. And obviously what we're forming is a mirror image. We can either form Y on the top and these groups will be pushed down, or we can form Y underneath and these groups will be pushed down. But because this is planar, the Y minus can attack from either above or below, and we actually form two different enantiomers from this. So just another thing on the enantiomers, thing as well is a classic example of an enantiomer is things like if you ever had spearmint before. So spearmint has a distinct taste, but and it has our carvone. It has carvone in there as well. So that's the chemical. But the other enantiomer actually exists in caraway seeds as well. So if you actually taste, caraway seeds are normally used in like cooking. So if you're making curries, for example, you use caraway seeds in there. But if you try it, if you can get caraway seeds, and if you get spearmint, say like chewing gum or something, and you can see, you can actually taste the subtle differences, I suppose, between the two. So yeah, or you can do it with oranges and lemons as well. They contain obviously they're both citrus fruits, but they also contain enantiomer, and you can taste the difference between there. So you can actually eat enantiomers. Obviously you can eat the different types, and not all of them are bad, but they can be. They can be, particularly if it's in medicines. Okay, so the type of enantiomer, just come back onto this. So the type of enantiomer formed will depend if the Y minus attacks from the top or the bottom, and it forms the following. So you can see there. So we formed both of our enantiomers there. Okay, so due to the planar nature of that carbocation, there is an even chance of the nucleophile attacking from the top and the bottom, and so this means we're likely to get a 50-50 mixture of both enantiomers. Hence, what we're producing here is a racemic mixture. So, as with all racemic mixtures, they do not retain plain polarized light, and so the rotation of plain polarized light is cancelled out by either enantiomer. So you can see the enantiomer on the left here, this one, could rotate, let's say, plain polarized light 5 degrees to the left. This one will rotate plain polarized light 5 degrees to the right. So if we have equal amounts of them, then the net effect is we get no rotation at all. So you've got to be really careful with that, because you might shine plain polarized light through a sample and it doesn't rotate it, and you might think, oh well, it's not polar, there's no chiral centers in there, or it's not a polar, there's no polar substances in there. Well, there might be. It just might be an equal mix. It might be a racemic mix. So don't automatically think that there's no chiral products in there if it doesn't rotate plain polarized light. You've always got to have in the back of your mind that it could actually be a racemic mix. Okay, so let's look at optical activity and reaction mechanisms for SN2 reactions. So let's look at a reaction between a primary halogenoalkane. So you'll remember this as well from the kinetics 2 topic, where we look at the different types of reactions, so SN1 and SN2. So primary halogenoalkanes go via SN2 reactions, and tertiary ones go via SN1 reactions. So you'll remember that from the kinetics topic. If you haven't, then go back and have a look, and you'll see a little bit more detail. But the primary halogenoalkane with a Y minus via an SN2 mechanism. So with an SN2 reaction, we have a single enantiomer producing one enantiomer, unlike the two that's produced under the SN1 reaction that we've just seen before, the mechanism. So in an SN2 mechanism, both the Y minus and the haloalkane, or the halogenoalkane, are reacting in one step, and the nucleophile always attacks the opposite side of the leaving group. Okay, so that's very important. So let's have a look. So before we do that, we produce one product, and this product will rotate plain polarized light differently to the reactant. Okay, so we can actually distinguish between the two and know if a reaction's occurred. So you can see here, there we are. So you've got your Y minus, lone pair on your Y minus. It attacks the carbon, but it always attacks from the opposite side to the leaving group, which is our halogen. As you can see on there, there's our halogen. So it comes in from the top, the halogen leaves at the bottom. So then we form this kind of intermediate, and the reason why we can do this is because we've got a lot of space around here, with it being a primary halogenoalkane. So this Y can squeeze in here. You couldn't do this with tertiary because you'd have methyl groups there, which are too big. So it can squeeze in here. So it forms this bond, and this bond breaks at the same time. So it all happens in one step. And obviously we form our haloalkane here, or halogen, or our substance, whatever Y is. It's not a haloalkane. So whatever this substance is here, might be a hydroxide, for example, which is an alcohol, but depending on what this is, it doesn't really matter. And obviously we produce our halide at the end. This all happens in one step, and we only form one product. We don't get a mixture of enantiomers like we did with the other one. Okay, so there's the stark difference between the two. But like I say, this is in the kinetics 2 topic. There's a lot more information on SN1 and SN2 reactions in there. Okay, so let's look at aldehydes and ketones. So this was the other area that we need to look at. So one of them was chirality. That was the first bit of the topic. The other bit is carbonyl, the carbonyl group, and the last bit is carboxylic acids. So let's look at aldehydes and ketones first. So aldehydes and ketones have a carbonyl functional group, which is that C double bond O. Okay, so that's pretty standard. So the difference between an aldehyde and ketone is pretty much the position of that carbonyl group. Okay, so is it going to be in the middle carbon, or is it going to be on a terminal carbon, so a one that's at the end? So aldehydes have the carbonyl group at the end, and they always have an ending of -al, so it's ethanal, methanal, propanal, etc. Okay, so here's an example. This is propanal, and you can see that carbonyl group is actually sat on the end carbon here, so that's called propanal. This one's called ethanal because we've got 2 carbons, so the nomenclature is the same. So we're looking at eth, and depending on the carbon chain, whether it's eth or prop or meth or whatever that is, depending on what it is, that's the same. Depending on the number of carbons, we just put al on the end. So fairly straightforward. Ketones, on the other hand, they have a carbonyl group on one of the inner carbons, and so these have the ending of -one. And sometimes we've actually got to identify where the ketone is with the number. So it might be, for example, pentan 2-one, for example, because it's sitting on the second carbon. But let's have a look. So this one's called propanone. So you can see the carbonyl group now is on one of the middle carbons there, so it's not on the end. So this is definitely a ketone. And here's an example. Here we are. This is pentan 2-one, and you can see that the carbonyl group, you can see it's sat here, is actually sat on the second carbon in the chain. So we've got to specify where that carbonyl group is with a number just before it. So yeah, so that's it's fairly straightforward, as you can see. Okay, so aldehydes and ketones, they have relatively low boiling points. Okay, so in comparison to alcohols, and this is because it's all down to intermolecular forces. Now, you would have seen intermolecular forces in year 1 chemistry. So if you're not too sure on intermolecular forces, such as, for example, London forces, then you need to go and have a look at that video here. But what we're going to do is look at these forces in relation to aldehydes and ketones. Okay, so aldehydes and ketones, they interact with each other via London forces and permanent dipole bonds, as there's polarity within the molecules. So we can see that actually, unlike alcohols, they have an OH group that can form hydrogen bonds. And remember the order, so it's London forces are the weakest, permanent dipoles are the middle ones, and then your hydrogen bonds are the strongest type of intermolecular force. So alcohols can actually undergo hydrogen bonding, so that means their melting and boiling points are going to be higher in comparison to aldehydes and ketones. So this means they have generally lower boiling points, like I say, for aldehydes and ketones compared to their alcohol counterparts. So let's have a look. So we've got propanal here. So this is an aldehyde, remember. It has a boiling point of 49 degrees Celsius. And your ketone, this is propanone, has a boiling point of 56. You can see it's quite similar to the propanal. But if you compare that with propan-1-ol, so similar mass, the boiling point is 97. So you can see it's a lot higher than propanone and propanal. And that's all because of them hydrogen bonds that can occur between alcohol molecules. Excuse me. Right. So aldehydes and ketones, they can hydrogen bond with water, though. Obviously, they can't hydrogen bond between themselves, but they can hydrogen bond with water. And so that means they have the ability to dissolve in water. So remember, for something to dissolve in water, it needs to be able to form interactions with the water. So let's have a look. So we've got the lone pair of electrons on the oxygen in that carbonyl group can form hydrogen bonds with the hydrogen atoms on the water molecules. And so here we go. Here's our example. So you can see here that we've got our carbonyl group here. This is in this case, this is a ketone, and it has a lone pair of electrons on the oxygen, and it can form a hydrogen bond with the hydrogen on the water molecules, as you can see there. And that effectively means that it is quite soluble. So smaller aldehydes and ketones will dissolve, larger ones with longer hydrocarbon components won't. And this is because the hydrocarbon component here, if this is a long hydrocarbon, remember this bit's insoluble. There's no polarity on hydrocarbon chains, so water can't actually interact with it. So if you've got a carbonyl group, if you've got a ketone or you've got an aldehyde, and it has a long hydrocarbon chain on it, then the bulk of that molecule is going to be insoluble. So the longer that chain is, the less soluble it is going to be in water. So if the aldehyde or ketone is large enough, then the London forces between the non-polar hydrocarbon chain will be stronger than the hydrogen bonding between the carbonyl group and the hydrogen on the water molecules, and this means that they won't dissolve. So it is all to do with the length of that chain, as I've just mentioned there. Okay. So how do we test for aldehydes and ketones? Well, what we can do is we can add acidified potassium dichromate, and you would have seen chromium chemistry in particular in the transition metals topic. So if you want to know a little bit more about chromium and how chromium's got loads of vibrant colours, so Cr2 plus Cr3 plus, obviously your dichromate and your chromium ion as well. So you've got loads of different varieties of chromium, but we're going to use acidified potassium dichromate here. And it can be used to distinguish between aldehydes and ketones. So acidified potassium dichromate, fundamentally, it oxidizes aldehydes, but it does not oxidize ketones, because ketones can't be oxidized. So let's have a look for aldehydes first. So these are oxidized using that acidified potassium dichromate, so K2Cr2O7. This is a mild oxidizing agent and is reduced itself, so you'll know if we have an aldehyde, because we'll get a color change. It'll turn from orange to green, which is your chromium ion, which is Cr3+. So ketones, these can't be oxidized, so there's no color change at all. So we can obviously distinguish between an aldehyde and a ketone, because if an aldehyde exists, we'll get a color change when using acidified dichromate of orange to green. But if there's a ketone present, obviously we won't see any of that at all. So the overall reaction, this is our ionic equation, or half equation should I say, is Cr2O72- reacting with 14H+, forming Cr3+ to 7H2O, with your 6 electrons in there as well. So remember, you are expected to be able to compose or write half equations. So we know that it's going from Cr2O72-, it's going to Cr3+. So you've got to be able to balance that using your protons, electrons, and water. You've got to be able to balance that as well. So that would have been done in year 1 chemistry, when you've seen how to do under the redox topic, I think, how to actually write a half equation and balance it. Okay. Another one is a Tollens reagent, and this can also be used to distinguish between aldehydes and ketones. This is a nice one. So Tollens reagent can be used, can be made first, should we say, and then that's going to be then used to test for aldehydes and ketones. So you can see here what we then do once it's made. We then add our aldehyde and ketone to the Tollens reagent, place it in a water bath. The reason why we use a water bath is because our aldehydes and ketones are flammable, and the last thing we want to do is to put a naked flame underneath a flammable liquid, because you're going to have some problems, obviously. So you can see here we put our test tube with our aldehyde and ketone into the beaker. Now a positive test is if we have an aldehyde present, we get a silver mirror. So we get silver coat in the side of the test tube. I told you it was a nice reaction. Ketones, you get nothing, unfortunately. The reason why is because Tollens actually contains a complex. It contains AgNH3 plus. So this is what's inside Tollens reagent. And it's got to be warm because that helps it to react. So it increases the kinetic energy of the particles and allows the reaction to proceed, to go over the activation energy. So the overall reaction, because Tollens is made by reacting silver nitrate and ammonia, so when reacted with the aldehyde, it reacts in the following way. So we need to know these reactions here. So we've got our our Tollens reagent here, which is our diammonium silver complex here, so diammonia silver. And we've got our aldehyde here, okay? We're reacting it with our OH minus ions. It's all dissolved in a basic solution, so that's where the OH minus comes from. Ag, obviously we form the silver, our carbonyl compound, so RCOO minus, then we've got our ammonia and water. But this can all be simplified by using AgNH3 plus an electron forms Ag and 2NH3. So you really need to know this reaction here, the simplified one, showing that actually we have our Tollens reagent here, and that's going to produce our silver solid. Obviously we get some ammonia produced as well. Okay. So Fehling's or Benedict's solution can also be used to distinguish between aldehydes and ketones. There's a lot of ways in which you can distinguish, can't you? So Fehling's and Benedict's are oxidizing agents, as is Tollens as well. But what they do is they oxidize aldehydes, but they won't oxidize ketones. So Tollens is also an oxidizing agent. I should add that at this point. So Fehling's and Benedict's solution is blue, as it contains copper 2 plus ions. And we add it warm to our aldehyde, then this blue solution goes to a brick red precipitate because we form copper oxide. But with ketones, it remains blue, so we get no color change because remember, ketones can't be oxidized, so we don't get any reaction. And obviously, you can see the test tubes there. So Fehling's, the main difference with Fehling's and Fehling's and Benedict's, they're very similar, but Fehling's is where copper ions are dissolved in sodium hydroxide. Benedict's is where the copper ions are dissolved in sodium carbonate. So they're very similar reactions. It just depends on what has been dissolved in. And so the overall reaction, as you can see here, the one that you need to know is the simplified version here. Effectively what happens is the copper 2 plus, receives an electron and forms a copper plus here. And obviously the copper plus is the red precipitate of copper oxide that we form here. So you can see the copper is effectively being reduced. It's gone from a 2 plus to a 1 plus. Okay. So aldehydes and ketones, they can be reduced as well. So we've looked at how we can test for them. So we can look at more chemistry on these. So aldehydes and ketones, they can be reduced to form primary and secondary alcohols. So reducing agents such as NaBH4, which is sodium borohydride, these can be dissolved in methanol and water, and they can reduce aldehydes and ketones. So it might be easier, and you may see this as well, you may have seen it already, is that actually it's common to use the symbol H in a square bracket to show a reducing agent. And so this is the hydrogen in the reducing agent, and that's why we use H. Just like you may see an O in a square bracket to represent an oxidizing agent. So that's, if you see the H in the square bracket, that's what it means. It just represents the reducing agent. Excuse me. Right. So here's an example here. So you can see here we've got our aldehyde. We're reacting it with 2 lots of reducing agent, and we're forming our primary alcohol. So ketones are reduced to secondary alcohols. So there we are. And that's reduced to secondary alcohol there. Now, the reason why we have 2 H's, as you can see here, is because we need 1 H to bond with the oxygen here to form your OH. And we need another H to bond with the carbon, which is on the side here. So there we are. So that's why we need 2 of these hydrogens, 1 to form OH and 1 to form the hydrogen and the carbon. So you've got to remember, you've got to be able to balance these reactions by using the reducing agents and the numbers in front of them. Okay, So let's look at potassium cyanide and the reaction with the carbonyl group. So we're looking at further reactions here. So we're looking at how we can test for carbonyl groups and how we can test for aldehydes and ketones. And we've also looked at how we can just going back, so how we can actually reduce the aldehydes and ketones as well. But we also need to know some reactions with certain chemicals. And this one we're going to look at potassium cyanide. So potassium cyanide reacts with carbonyl compounds to produce hydroxynitriles. Okay, so this reaction occurs via nucleophilic addition. So remember, a nucleophile is nucleus loving. Okay, so it's a nucleophilic addition mechanism. So this means the nucleophile, so in this case it's going to be a Cn minus. This attacks the carbonyl group, and remember that carbon on the carbonyl group has a delta positive, so your cyanide is going to be attracted to that because it's negatively charged. It adds on and it makes your hydroxynitrile. Hydroxynitrile is very simply something that contains a Cn group and an OH group as well, so hydroxynitrile. So potassium cyanide is used to produce the Cn minus ions, okay? And when it's dissolved in acidic solution, it dissociates to form K plus and Cn minus. So you can see here that we're using potassium cyanide, and we get our cyanide ions from there. So that's our source. So here, the cyanide ion comes from the potassium cyanide, is the nucleophile. Okay, so it's nucleus loving. And you can see what's going to happen here is the electrons from the carbon attack the delta positive carbon, so it's a nucleophile, and effectively the lone pair of electrons are donated to it. So then what happens immediately is, because effectively we're forming too many bonds around the carbon, is one of the double bond starts to break, and so two of the electrons in the double bond, these transfer to the oxygen at the top. So hydrogen cyanide can be used as well, and if we are using hydrogen cyanide, we don't actually need to dissolve it in acid because hydrogen cyanide is acidic in its own right. It's easier to use potassium cyanide because it's less toxic. It's easier to handle. Hydrogen cyanide is a gas, and you definitely need to use fume cupboard for hydrogen cyanide. And also, the cyanide molecule is quite difficult to use as well, in terms of like the handling of it, because it's a gas. Okay, so as the potassium cyanide used is acidified, then what we have is a supply of H plus ions already in solution. And so the intermediate that we formed there with the O minus, the electrons on the oxygen actually are attracted to the H plus ions that are existing in solution. And so what we then form is our final product, which is our hydroxynitrile that is formed there. So you need to know the mechanism for this, and you need to know obviously what's attacking where. You need to know that your cyanide is your nucleophile, and you need to be able to name the compound, and identify the compound at the end. So the overall generic equation for the reaction with an aldehyde is RCHO, so this is your aldehyde, reacting with potassium cyanide and obviously dissolved in acid, so it's H plus ions, will form your hydroxynitrile, and potassium ions are produced at the end. And then for ketone, you can see here, there's your ketone, reacting with potassium cyanide and H plus. The only difference with the ketone is that your hydroxynitrile is not going to be on a terminal compound, it's going to be in a middle compound instead, a middle carbon, instead. So that's the only difference there. The reaction, though, is the same. So if we use an unsymmetrical ketone or aldehyde, so apart from methanol, okay, we get a mixture of enantiomers is produced, and we've seen optical isomers, and obviously we'd seen that in earlier on, so within this topic, but you'd seen that obviously earlier on before. Okay, so we use potassium cyanide. When we use it, we need to assess the risks when using it. So remember I was talking about using potassium cyanide and hydrogen cyanide, and I said that potassium cyanide is probably less risky to use than hydrogen cyanide because it's easier to handle. That doesn't mean that there are no risks at all for potassium cyanide. So we need to be aware of these. So let's have a look at what these are. So potassium cyanide is an irritant. It's very dangerous if ingested and inhaled. Not very good at all because it contains the cyanide molecule, which is clearly lethal to if it's ingested. And when potassium cyanide reacts with moisture, it can form that toxic gas of hydrogen cyanide. So we've got to try and keep it as dry as possible because we don't want hydrogen cyanide just floating around in the atmosphere. So to reduce the risks associated with handling of potassium cyanide, the user needs to do the following. Some of these are obvious. So we need to wear gloves when handling it to avoid contact with the skin. We need to wear safety goggles. We should do that at all times anyway. We need to wear a lab coat to prevent clothing contamination. And we need to use a fume cupboard to prevent exposure to toxic fumes. So we're trying to reduce the exposure of this gas. Okay, so we've looked at how we test for aldehydes and ketones, but what we can do is test just for the carbonyl group in general, whether it's an aldehyde or a ketone. And a way in which we can do that is using Brady's reagent, or 2,4-dinitrophenylhydrazine. Try and say that quick, which is 2,4-DNPH, and it can be used to identify that carbonyl group. So Brady's reagent is dissolved in concentrated sulfuric acid and methanol, and then it's added to the substance under test. And so if a carbonyl exists, what we get is a bright orange precipitate is formed. And this actually only reacts with the carbonyl group in aldehydes and ketones. It doesn't react with the C double bond O group in carboxylic acids. So that's really important because this allows us to identify carbonyl groups, either an aldehyde or ketone, but doesn't actually identify for a carboxylic acid. So the orange precipitate that we actually form is a derivative of the carbonyl compound, which is purified through recrystallization. So we form this powder. Now, depending on the aldehyde or ketone that we've actually had in there, that could be ethanol or propanol, for example, or butanone, then this is obviously going to form a different type of orange precipitate. And the orange precipitate is unique to the aldehyde or ketone that we've used. And so for this reason, what we can actually do is extract this recrystallized and purified solid and run it under a melting point apparatus. And actually, the melting point of that solid will be unique to the aldehyde or ketone that we've tested it with. So it's a really good way of actually trying to identify our compounds. And we just, obviously what we do is we take the melting point that we've obtained from practical sources and we compare that with a library of known sources. So that may be in a data book, for example. Okay, so carbonyl groups, that have a methyl group attached, so a CH3, they actually react with iodine as well. So we need to know all these different types of reactions with the carbonyl group. So if we heat iodine in the presence of an alkali with methyl carbonyl group, then we'll be able to produce a yellow precipitate called triiodomethane. Okay, so a methyl carbonyl group only exists in the following circumstances. So either in ethanol, as you can see here, or in ketones with a methyl group that's directly bonded to it. So this is a methyl carbonyl group. So we're looking for these strict circumstances here. And if that exists, then it will react with your iodine. So let's have a look. So the overall equation here we've got our methyl carbonyl group here reacting with iodine, and it's obviously all dissolved in an alkaline solution as well. So this is forming our yellow precipitate or triiodomethane molecule here, and so therefore we get this yellow precipitate that's formed. So what you need to be aware of is that if you see any reaction like this or any setup like this and it's reacted with iodine, that you will form a yellow precipitate, and that yellow precipitate is triiodomethane. So that's the main points there. It's all nice and colourful, all this. Okay, so looking on to the next section. So remember, there's 3 sections to this, and so the one was carbonyl groups, the other one was chirality, and the other section was carboxylic acids. And so this is where we're going to look at carboxylic acids here. So carboxylic acids, they have the carboxyl group, which is the COOH functional group, which contains both the carbonyl group, which is the C double bond O, which we've just seen before, and a hydroxyl group, which is clearly our OH group as well. So carboxylic acids are named by finding the longest carbon chain, and then we add oic acid at the end. So it's very straightforward. Very similar to aldehydes and ketones, where we find the longest carbon chain, and we add either al or one on the end. Here we're adding oic acid. So when we're naming carboxylic acids, the carbon on the carbonyl on the carboxyl group is always carbon 1. Very important. So it's always at the end. Like I say, the carboxyl group is always at the end of the molecule. So let's have a look at some examples. So we've got ethanoic acid here. So the reason why it's eth is because we've got 2 carbons and we add oic acid at the end. This one, a little bit more complicated just to show you how it works. But 4-chloro-3-hydroxybutanoic acid. So it's butanoic because we have 4 carbons in the chain. We have, this is always labelled as carbon 1, always. So it's 1, 2, 3. So it's 3-hydroxy, 4-chloro, as you can see there. So that's just to show how it can be named, making sure that the carboxyl group is always carbon 1. So that doesn't change. So that makes your nomenclature easier, actually. And you might get some phenyl-based compounds as well, which is benzoic acid. And actually, you'll see benzene-based chemistry in chemistry 3. Organic chemistry 3 topics, so that's topic 18. So you'll see a lot more of benzyl or benzene in that topic there. Okay, so carboxylic acids, they can hydrogen bond, so very similar to what we're looking at with aldehydes and ketones, where they can hydrogen bond to water molecules. Carboxylic acids can also do that as well, and so therefore they can dissolve in water. So what we have, as you can see here, we have a lone pair of electrons on our carboxylic acid molecules here. There's a carboxylic acid, there's another carboxylic acid, and this is interacting with the water molecules that are floating around. So we still have this hydrogen bonding ability. So you can see that just like with aldehydes and ketones, only smaller carboxylic acids will dissolve, and the larger ones have longer hydrocarbon components and are non-polar, and this can actually disrupt the hydrogen bonding within the molecules. So the same rules apply. So there's nothing new here. We're just adapting it to a different molecule, that's all. And also dimers can form when we have a pure liquid form of a carboxylic acid. So a dimer is just where the carboxylic acid hydrogen bonds with each other. And so the net effect is actually the boiling point increases as the joined molecules are larger, and so the intermolecular forces are greater. So that's quite a unique property for carboxylic acids, is that they can form these dimers, and that gives you a higher boiling point because they can actually kind of interact with themselves, mainly because they've got hydrogens and oxygens which are spare. Obviously they've got a hydrogen here as part of the hydroxyl group and the oxygen here, so they've got numerous ways in which they can interact, so they can form these dimers. Okay, so how do we make carboxylic acids? So carboxylic acids are made from nitriles, aldehydes, and primary alcohols. So let's have a look. So primary alcohols and aldehyde are oxidized to carboxylic acids using an oxidizing agent. Okay, so we've seen that before, such as potassium dichromate. So you can see, there we are. So we start with our primary alcohol here. So there's our primary alcohol, oxidizing agent, forming our aldehyde, and then oxidizing agent. We can keep on doing this. It's all done under reflux, and then we form our carboxylic acid at the end there. So carboxylic acids are also made by the hydrolysis of nitriles. So there's our nitrile, reacting it with water, hydrochloric acid, an oxidizing agent, and we form our carboxylic acid and ammonium chloride as a product. So you need to be aware of how to make this, particularly in things like organic synthesis, which you'll see later in topic 18. You'll see about organic synthetic routes. So it is important that you need to know how we make carboxylic acids and what reagents we need and any intermediates that are formed. So for example here, this is obviously a primary alcohol. We're forming an aldehyde, and then that aldehyde can be oxidized further to form a carboxylic acid. So you can see this is a two-step synthesis. Okay, so we need to know some reactions of carboxylic acids as well. And so carboxylic acids are weak acids. They have the word acid in there, and they do react with carbonates to form carbon dioxide and bases, and they form salts. So carboxylic acids, they're weak acids, which means they dissociate partially to form the H plus ion and the carboxylate ion. So they're not strong at all. Strong acids would dissociate fully. These are weak acids. So you can see here, there's our carboxylate ion there. So we've got a carboxylic acid that's in equilibrium with our carboxylate ion, which is here, and obviously H plus. So the equilibrium lies to the left as it dissociates poorly. So remember from equilibrium topics that equilibrium of weak acids lies well to the left. We've got large amounts of this here and not much of these ions here. Particularly if you would have seen the acid-base equilibria in particular, that topic where we looked at buffers, then this bit is obviously looking at, so when we're looking at buffers, this is clearly relevant because we use a weak acid and its salt to make the buffer, so therefore you would have looked at equilibrium there. Okay, so as they're acids, they react with carbonates, so that's CO3 2- ions, and they form a salt, carbon dioxide, and water. So let's have a look. So the reaction between ethanoic acid and sodium carbonate. So we can see here, there's our ethanoic acid there, reacting with our sodium carbonate, and that produces our salt plus water plus carbon dioxide. So we're forming our salt and carbon dioxide and water from reacting it with a weak acid. This is a standard acid carbonate reaction, so you need to know that when you react an acid and carbonate forms salt plus water plus carbon dioxide. That's quite standard. And then the reaction between ethanoic acid and sodium hydrogen carbonate is another type of example. Again, very similar reaction. We form salt, water, and carbon dioxide. We're just using sodium hydrogen carbonate instead. So it's a very similar reaction, as you can see. And so the reaction between ethanoic acid and sodium hydroxide, so this is acid-base reaction, we just form salt and water, as you can see on the bottom there. So we're using ethanoic acid, sodium hydroxide, and that will form sodium ethanoate and water, as you can see in the reaction on the red box. So you need to know all these reactions. You need to know they are an acid, so you need to know your basic acid-base reactions. So carboxylic acids, they can be reduced to alcohols, and they can also be reacted to form acyl chlorides as well. So let's have a look at these. So carboxylic acids, they can be reduced. However, we must use a powerful reducing agent such as lithium aluminium hydride, so LiAlH4, and we've got to use a dry ether solvent as well. Now you can see in this reaction that we have our carboxylic acid here reacting with 4 lots of reducing agents, and obviously that will form your primary alcohol here, which in this case is ethanol. And obviously we use water. Water as a reagent as well. So if we react a carboxylic acid with phosphorus 5 chloride, so PCl5, then what we can do is we can produce an acyl chloride. Okay, so you can see here that we've got our carboxylic acid. This is a slight mistake, which will get changed. This should be a Cl on the bottom here because it's an acyl chloride is formed, and obviously reacting that with the PCl5. So this is an acid chloride. So emphasize again, this OH should be a Cl. So that's a typo there. Okay, but that will get changed. Okay, so formation of esters. This is an esterification reaction. Okay, so you might have done this in the lab. So if you're in a school or college, then you might have actually made esters using this method. But if we react alcohols with carboxylic acids and acid anhydrides, they can be used to make esters which have the COOO group in there. So an ester is produced when we react a carboxylic acid with an alcohol and sulfuric acid catalyst under reflux. Okay, so you might have done this under reflux, or you might have done this in a beaker, depending on what type of esters you're forming. but it's always better under reflux because you get a better yield because you're able to heat it. So carboxylic acid plus our alcohol, as you can see here, that will produce our ester and water. So this is all done under acidic conditions. Okay, so carboxylic acid plus alcohol forms ester plus water. And we can separate the ester through distillation. So we use a distillation kit. However, this must be done in situ as the reaction is reversible, as you can see on there. So it means it will go backwards. So as soon as it's formed, you must separate it using distillation. So to purify the ester further, what we can do is add sodium carbonate, and this removes any carboxylic acid that may remain. So remember, this reaction is in equilibrium, so you may still have some carboxylic acid left over mixed in with your ester. And so the layer on the top after the addition of sodium carbonate solution is the ester, and obviously this can be separated using a separating funnel as well. So it's a way of just, once you've established your ester, it's a way of trying to purify it and making sure you've got a pure sample, because that's quite important. So esters, we need to know how we actually name an ester, and they're named in two different ways. So two sections, sorry, not two different ways. So the first bit is from the alcohol, whatever the alcohol was used to make the ester, and the second bit is named from the carboxylic acid that was used to make the ester as well. So let's have a look at this example. So here we've used ethanol and propanoic acid. So what we're going to do is we're going to, obviously we've got the formula there drawn, but we're going to name the compound using the naming. So the first bit of the ester is formed from the alcohol group, and this is the alkyl group on the end there. So in this example, it's ethyl, and so this is named first when we're naming an ester. So that has come from the alcohol you can see in red there. The other bit, this is the blue bit, this has come from the carboxylic acid, and you can see that to an extent. And so we remove the oic acid bit from that and replace it with OAte. And in this example, this is propanoate. So in this case, this is named second. So what we're looking at is the full name is ethyl propanoate. So ethyl coming from your alcohol, this is in the red here, and your propanoate coming from your carboxylic acid part, that's in blue. So here's another one. This is reaction with ethanol and 2-methylpropanoic acid. So you can see here that we've complicated it a little bit because we've added a methyl group onto this carboxylic acid. So when we name esters with alkyl branches, as we can see there, we number from the carbons in the COC part of the molecule. So you can see here, this is going to be carbon 1 and carbon 2. And this is going to be 1, 2, and 3. So this part of the ester, like I say, is formed from the alcohol, so it's the ethyl part. And this part of the ester is formed from the carboxylic acid. So this example, it's 2-methylpropanoate, and it sits on the second carbon, your methyl group, as you can see on there. So the full name is ethyl 2-methylpropanoate. So just make sure you're following them rules. You name it with the alcohol part or the ethyl bit from the alcohol first, then it's the carboxylic acid part, and obviously make sure your numbering is correct as well. You always number from the COO or the OCO group there, so you can see how we've numbered it. So if you do have any methyl groups or alkyl groups hanging off it, then you'll be able to name them correctly. Okay, so esters are used commercially in industrial processes, so they are actually very, very useful. So perfumes and food flavourings, they're used commonly in there. So some esters have a sweet smell, they're really nice. If you've done it in the lab before, then you'll know what I mean. So you can get things like pear drops, for example, and this makes them ideal in things like fragrances. Obviously, fragrances are obviously things like perfumes. They've got a obviously they can have a sweet smell depending on obviously what type of perfume you're forming, and they're also used in food products as well. So to make food flavourings, for example, you might see them as E numbers on the back of a packet. Solvents, so esters are polar, so and so other polar compounds will dissolve readily in these esters. They have low boiling points, they evaporate easily, so this makes them ideal for using glues because you want it to be liquid when there's no air, but in contact with air you want it to evaporate and leave the hard resin behind. So that's effectively what a glue is. And plasticizers as well. So esters are used to make plastics much more flexible during that polymerization process. They can leach out of the plastic over time, and the plastic does become brittle. So you've got to be careful. Obviously, the plastics don't last. They don't last forever. Well, in some respects, okay. So they do break down. So it depends on obviously the plasticizers will leach out of it. Now, there's been instances as well where certain plastics have the plasticizers leaching out, and this could be particularly for small children's toys where they put them in the mouths. They've got to go through strict testing to make sure that these chemicals don't leach out and go effectively into our bodies. That could be the same as plastics in, for example, plastics in food packaging when we're cooking things in plastic tubs. So we've got to be careful of when we're heating them up, for example, of plastics leaching out. So we've got to engineer these plastics carefully and use the right chemicals. Okay, so esters can be split up using water, and we call this hydrolysis. So hydro meaning water, lysis meaning to break. So we're breaking with water. Now, these processes of hydrolysis of esters can be sped up using an acid, so we call it acid hydrolysis, or we can use a base called base hydrolysis, so we can react using with a bit of help from an acid or a base. So let's look at acid hydrolysis first. So here we use dilute acid to split an ester into a carboxylic acid and an alcohol. So we can use sulfuric or hydrochloric acid, and the reaction is, of course, conducted under reflux. All of our substances here are volatile, and so therefore reflux allows us to heat volatile compounds up, but without the risk of losing them into the environment. So let's have a look. So you can see here there's our ester, and we're going to obviously use water because it's hydrolysis, and this is ester hydrolysis, so acid hydrolysis. So we're going to use an acid here as well. And that forms our alcohol, our carboxylic acid. What I've done is I've color coded it so you can see where things are coming from. So you can see here, this is the red section here, is that bit there, and two of the OHs from, an OH from the water adds onto the bottom here, and then obviously the other bit is the alcohol, and you can see the blue bit. So it's all color coded. So the blue bit comes from the acid, the ester, and the H, the green H, comes from the water that we've added in there as well. So the addition of water, so if we add more of this, shifts equilibrium to the right, so more product is produced. So as long as we keep replacing the water and adding more of that, equilibrium will shift to the right to use it up. So remember Le Chatelier's principle. Seemed a while back, didn't it? Okay, so we can also use it for base hydrolysis as well. Similar reaction, except we're going to use a dilute base to split the ester into a carboxylic acid and your alcohol. And here we're going to use something like sodium hydroxide. Again, it's all conducted under reflux. So the reaction goes like this. So we've got our ester, but notice we have an OH minus group here, so it's base hydrolysis. And we form our carboxyl ion here. And then obviously our alcohol is formed as well. So this is just an example of a base hydrolysis. Obviously, it's all in solution. Okay, so let's look at polymers. So polyesters are formed by reacting a dicarboxylic acid and diol together. So polymers are very important because they form the plastics that we have, the clothing that we have, and it's all pretty much dependent upon it's all organic chemistry, so organic molecules joining together to form a long carbon chain. So here we're going to be looking at polyester polymers, and esters, as it says the word ester in there, we're using a carboxylic acid and an alcohol, but because we're forming a polymer, we've got to use a dicarboxylic acid and a diol. And what we do is we react these together and we form an ester link. So that's the ester bond in the middle. And this is when a dicarboxylic acid reacts with a diol. So a dicarboxylic acid is, as it suggests, it's a carboxylic acid, but the word di means it's got two in there. So we've got two carboxyl groups either side of an R group in the middle there. So this is a dicarboxylic acid. And then we have a diol, which is basically a alcohol with two OH groups either side. And so when we react them together, we form our polyester. So a polyester has our ester link in the middle there. But the reason why we need a diol is because we need a group at the end, either side of that link, to then react with another. So this will react with another carboxylic acid, and this bit would react with an alcohol. So it allows us to keep adding bits to this chain and hence form a polymer. So that's why we must use dicarboxylic acid and a diol. And you can see here, water is eliminated here. So we call these a condensation polymerization. So water is eliminated. So terylene is a polyester that is used in plastic drinks and sheeting clothes, and it has an acronym PET. So this is a specific example of a polyester polymer. And terylene is made from benzene 1,4-dicarboxylic acid and ethane 1,2-diol. And if we join these two together, then obviously we form our terylene. So benzene 1,4-dicarboxylic acid looks like that. So again, you've got your benzene molecule there, and you've got your two carboxyl groups either side. And your ethane 1,2-diol it's ethane, so it's two carbons with two alcohol groups either side. And then we form our terylene, and you can see a terylene molecule is quite a big molecule, a bit bigger than the other one that we'd just seen there before. And we have an N here. The N bit here tells us that we have a number of these repeating over time. So and we also obviously form two lots of H2O because it's a condensation reaction. So let's move on to I suppose the last part to do with the derivatives of carboxylic acids and carboxylic acids. So acyl chlorides, also known as acid chlorides, or AKA, they have the functional group COCl, which contains the acyl group, so the COCl group. So acyl chlorides are named by finding the longest carbon chain and then adding oil chloride on the end. Okay, so we've seen this a little bit before in one of the previous earlier on in the video. So when naming acyl chlorides, the carbon on the acyl chloride is always carbon 1. So this looks familiar because this is exactly how we would name a carboxylic acid. And of course, it's always got to be at the end of the group. Again, you can see very similar to a carboxylic acid. So here's an ethanol chloride here. So ethanol chloride is very similar to a carboxylic acid, except instead of having an OH group at the end there, we have a Cl atom at the end. Here's another one. I've complicated this one a little bit more. So you can see I've added a few things onto the carbon chain, but just to show that you can name it in the same way. Remember that when we're numbering them, we'll always start from carbon 1 here, and that's 2, 3, and 4. So this is going to be 3, 4 dihydroxy. Okay, so this is them here. So that's carbon 3 and carbon 4. 2 methyl butanoyl, because we've got 4 carbons, chloride, because we've got the chlorine in the end. Okay, so you can see the nomenclature of them is very, very, very similar to carboxylic acids. So there's nothing new here. So acyl chlorides, these react with water, ammonia, alcohol, and primary amines. And in each reaction, the chlorine is being substituted for either an oxygen or a nitrogen, obviously depending on what you're reacting it with. So let's have a look at the reaction with water. And so if we take an acyl chloride or an acid chloride and react it with water, we produce a carboxylic acid. So let's have a look. So you can see there's our ethanol chloride, which is there, and this is going to react with water. And what this does is it produces a carboxylic acid and obviously hydrogen chloride gas. Now what you'll see is this reaction is incredibly vigorous. It's a really, really reactive reaction. We have a very strongly delta positive carbon here because we've got 2 electronegative elements pulling electrons away from that carbon. So it's a vigorous reaction, and we also see white misty fumes of hydrogen chloride gas being produced here. So that's the key, that's what we see there. Also I've color coded it so you can see where the atoms are going. So you can see we've got a red section here. This is the CO and the Cl. So the CO remains on the molecule, the Cl comes off, and obviously you can see how the water then interacts there. So let's have a look at the reaction with ammonia. This produces amides. So here is our acid chloride, and this time we're going to react it with ammonia. So this is ethanol chloride. Again, all color-coded so you can see where they're going. And you can see we produce our ethanamide here and HCl as well. Again, it's a vigorous reaction. We've got to be very careful with HCl. It's a toxic and acidic gas, so we don't want to be breathing that in. Okay, so let's have a look at the reaction with alcohols. These produce esters. So you can see here there's our acid chloride, ethanol chloride reacting with, in this case, methanol. And this is going to form methyl ethanoate, so we formed our ester, and again we produce HCl gas. And finally, we react it with primary amines to produce N-substituted amides. So here we go. Here's our ethanol chloride, and we're reacting it with a primary amine. So that's the one in blue there, and this forms our N-substituted amide. So what's a little bit different about this is an amide because we've got an NH near a carbonyl group, so that we definitely know that's an amide. But the reason why we say N-substituted is because on the N here, one of the hydrogens, if that was a traditional amide, you would have NH2. But one of the hydrogens has been substituted, you can see there, for a methyl group. So the N bit stays there, but the substituted bit, when we say substituted, that is where you write the name of the molecule that substituted the hydrogen that would have otherwise been there. So this one is N-methyl, because we've got a methyl group there attached to the N, and this is ethanamide because we've got the 2 carbons there. Okay, so that's how you name it. And that's it. So that's everything on topic 17, Organic Chemistry 2. I hope that was helpful. There's a lot of reactions there. But the key thing, like with anything, is just practice, practice, practice. Keep practicing and come back to this video if you need any further help. Like I say, there's a full range of videos on here for organic chemistry. Just have a look on the Allery Chemistry YouTube channel. You see loads of videos for the full EDEXCEL range. They're all for free, so all I ask is that you hit the subscribe button. That would be fantastic. And also, these are available to purchase if you want your own copy of these. Very straightforward. Click on the link in the description box and you can get a hold of them there. Okay, that's it. Bye-bye.